So, hey everyone. Thanks for coming to my talk, Auditing Data, and answering that lifelong question, is it the end of the day yet? Now, if you're not familiar with that question, don't worry about it, because we're going to go deep into it in the next 60 minutes. So, what are we going to talk about in the next 60 minutes? We're going to start with Nielsen's architecture, and we'll really see how it had little fires everywhere. And I'm going to convince you why we had that need for a data auditing system. We'll then go into designing that system and talking about how even data auditing data looks like, how to store it, how to query it. Then we'll finally maybe get an answer to that question, is yesterday over? And then some alerts and add-ons, because that's always fun. But first, the most important thing, who am I? So who am I? I'm Simona. I'm 29 years old. I work at ADOC as a big data engineer, but I did work at Nielsen up to a few months ago, so this is totally based on a true story. I've been dealing with data for the past 10 years now, which feels like a lot. I love music, the weirder the better. I love Japan, and I love traveling. So this is basically me in a picture. So the first thing to keep in mind when you look at Nielsen's architecture is that this architecture receives and processes more than 50 terabytes of data per day. We're talking about billions of events that we collect from various devices. So that includes cell phones, TVs, computers. And all of these events, they get eventually, here's my laser, they go straight into the data serving servers. And those servers, they're included in that front-end layer. What's important to keep in mind about those are they're written in Java. SLAs are very, very important to them. And another point is that the entire front-end layer is regional. So at the time that we've designed this architecture, which was like a year and a half ago, we had several data centers all across the world. And each one of these data centers was running its own front-end layer. So the data serving servers, they receive all that data, they enrich it, and then they produce it to their own local regional Kafka. From there, the data gets replicated using a uReplicator into that one central Kafka in AWS. And we're talking about Kafka that's 50 brokers big. From there, we have Spark streaming applications that we personally call the data loaders. They consume that data, they deserialize it, and they spill it straight into RDR. Now, RDR stands for Raw Data Repository, and it's basically our data lake on S3. From there, we have our Spark jobs. They run periodically. They, again, consume that data, enrich it, aggregate it, and eventually store it in all of these different data stores, right? So we have MySQL, we have Postgres, we have Druid, and even back into RDR. And each one of these data stores is serving an entirely different need, an entirely different application. And if we look at the application layer, each one of these applications can consume that data straight from that set data source or altogether through Hive. And so this architecture really had little fires going on everywhere, especially in data latency-wise. And really, at this point, let's start discussing all of these data arrival pain points. So the first thing I want to do is really zoom into that connection in between the regional Kafka and the one central Kafka in AWS. So if you're not familiar with the uReplicator, it's a project by Uber. It's based off of Kafka's own mirror maker. And it essentially suffers from the exact same set of problems because of the way that the mirror maker was implemented. So what kind of set of problems am I talking about? So the most straightforward problem would be the uReplicator crashing, right? So the uReplicator crashes, then data does not flow, data is not being replicated anymore from that regional Kafka into the Kafka AWS. But there are problems that are a lot worse. So let's say that you have a pretty big Kafka topic. And I'm talking about topics that are 1,500 or 2,000 partitions big. So what would happen is that the uReplicator would stop replicating, but not on all of the partitions. So it would stop replicating on some 10 or 50 or 100 partitions. So most of your data is flowing, and you're essentially not even aware that there's a chunk of that data that's actually not being replicated. So next, let's talk about what happens actually after the data arrives into the Kafka on AWS. So what could go wrong here? Well, let's say that one of the Kafka brokers started crashing, or the entire Kafka cluster is unavailable, or the data loaders are crashing, alerts are popping up, we have to go and check what's wrong with the data loaders. Essentially, data is not arriving into RDR. It's again being late. So these were essentially our pain points in this architecture, but the thing that I didn't actually discuss is how do we recover from these failures? What would be our criteria to, well, okay, something crashed, data is not arriving anymore, but things are okay now. So if we go back again to this connection between the regional Kafka and the Kafka on AWS, the uReplicator crash is not working anymore, we started it back up again, data is flowing again, well, then that's great, problem solved. And if we look at this point, right, so Kafka brokers crashing, or the entire Kafka cluster is not available anymore, our data loaders are crashing, we just started them up again. Data is flowing in again, so problem solved. And at this point, we had no actual information in regards to the implications of all of these crashes on our data integrity. And Nielsen's a data company. Data is very, very important to us. Data integrity is very, very important to us. And we didn't really have all of that information in regards to the way that our data makes through all of these points in this waterfall and the implications of these crashes on our data, on data loss and data duplication and data latency. And at this point, I really want to start discussing this question, the end of the day question. And to understand the importance of it, we really need to talk about the use of data in the media world. So what interests us in the media world, in Nielsen's world, is daily data. Because we want to count users, unique users, on a daily basis. So when we run our processors, and I told you that we run our Spark jobs periodically, we essentially want to run them on 1 day's worth of data, on yesterday. So if data is late to arrive, and you run your processor on a partial amount of data, then you'll have to rerun the processor again, right? And that would cost you quite a lot of money. So we tried solving this problem at first with some legacy solutions. We said, okay, we use Airflow as our scheduler. When's yesterday over? Let's trigger our job then. Right, so when would yesterday be over for sure? Let's say 11 a.m. 11 a.m. sounds really good. So we set our Spark jobs to run at 11 a.m. And then we had this day with a peak of data. The data loaders were not really set up to the job of consuming all that data. And so we had a data latency problem. Data was not arriving in time into RDR, and not the entire day of data did arrive actually by 11 a.m. So the day was not actually over. We said, okay, so the fixed time solution is not a good enough solution. We need a better indicator. What kind of indicator we can use? Well, let's do AWS S3LS. Because, you know, let's see, if data was not written to that day's bucket for like 2 hours, then yesterday's over. The day's over, that's fine, and we can run our Spark jobs. But then we had a really bad Kafka outage. It was out for hours. And so the data processor started running again on a partial chunk of data. So all of these solutions were not good enough. And if we talk about all these pain points, again, in the context of this architecture, I think you'll really see what I'm talking about. So Kafka's crashing, or Kafka's not available at all, the data loader is crashing. Essentially, data is being late arriving into RDR. The data processors are not aware. They start running. They process that partial data. They store it in all of these different data stores. And so we have to reprocess that data, right? But the problem is not over yet. Because if we talk about the application layer, then all of these applications that consume that data, they not only consume it, some of them create their own data sets. So they as well have to, again, reprocess, run again. And so if we look at this architecture again, I think you'll really see that we had little fires going on everywhere. So for all of these reasons, for all of our data arrival pain points, and also for solving that end-of-the-day question, we decided to design our auditing system. And so what we'll do now is actually just start designing our data, understand how it looks like, understand how we're going to produce and consume it. But first, I really want to go through some points with you guys. And these points are really important to keep in mind while we go through that process. So what are these points that we should keep in mind? The first point is going to be that we do not have only one Kafka topic. We had several of them. And not only that we had several Kafka topics, this number was not fixed either. So if tomorrow there's a new need and a new application, we're probably going to define a new Kafka topic. The next set of points to keep in mind really have to do with the data serving servers, and I've actually mentioned some of them before. So the first would be, in the second bullet, is that they're implemented in Java, and not only that they implemented in Java, each one of these servers is running 2 JVMs. And each one of these JVMs is working against a set of topics. So they get data, they don't really care what data they're getting, they're enriching it, and then they're shipping it to the relevant topic. The second point that I want to talk about is that we were using our own Nielsen Kafka producer, which is a Kafka producer with some Nielsen add-ons. And we've decided to implement this auditing system on the Nielsen Kafka producer. And if we think again about the fact that SLAs were very, very important to us, then we really had to implement this code in an optimized way, so not to interfere with data serving's SLAs. The last point to keep in mind is that we use Avro. So we use Avro for serialization, and this will actually make our job easier. So what's the word window? Why is it written on my screen right now? So if you think about all the points I told you to keep in mind, and look at this auditing window, which is essentially our auditing metadata object, you'll really see how they all make sense. So we have our topic, our server, and process, right? So for every server, for every process, for every topic, we're going to count the amount of messages that are being produced. So what is the word window? Well, essentially, you can't really audit forever. So you have to really define a time frame. We've defined it to 5 minutes. Why? Well, 1 minute, that sounds like not a lot, and 1 hour sounds like too much. So we said, OK, let's go with 5 minutes, and we're going to implement it in such a way that you can really just reconfigure it later on. We never did. 5 minutes was great. And what you see before you right now is also the Avro definition of that metadata object, of that audit window object. Cool. So what we need to do now that we actually have that count and we have that metadata object, is just connect it to our data. So what we're going to do is we're going to create an audit header. So the audit header will have all that complementary information that our data does not have. So what do we have? We obviously have the topic, because we're consuming that data off of some topic. We do not have the server name and the window timestamp. If you're wondering about a sequence ID, that's a bit of a spoiler, and we're going to talk about it later on. Now, the question is basically how we're going to inject that audit header into our data, and that's what we're going to discuss right now. So if we look at an anonymized version of an Avro definition of a topic that we had, you can see several fields, right? And you can see that the second line now includes audit header. So we've just added that audit header object to all of our Avro schemas. So now all that we have to do is just run over that field in our Avro definition in our code. So what's going on here? OK, so what's happening here is that we're receiving some sort of data. We're not really sure if auditing is enabled on it or not. So the first thing that we're going to do is just check if it includes the audit header. If it does, then that's great. We're just going to run it over with an object that we've created. And that way, if our auditing data does include an audit header, it will now include all of that information that we need. So now that we have all of that information, we just need to produce it somehow so that we can consume it on the other side. So with our data, that's pretty straightforward, right? Our data is just keeps flowing through the system now with an audit header. So it's going to go through Kafka just as it used to. And what we did with the audit metadata object, we started producing it to its own audit metadata topic. Cool. So I think you've noticed that we have a bit of a problem here, right? Because we're actually auditing Kafka with Kafka at this point. And we've noticed that problem as well. So what we decided to do is just implement a simple REST service using Amazon API gateway that's going to receive that audit information, the audit metadata information, straight from the server. But then we had to choose. We said, OK, we already have that Kafka topic implemented, and now we also have that API gateway implemented. And we decided to stick with both. And if you're asking yourself why, it's A, because the Kafka solution was already working and was already there. And then we also felt that just using both of these ways to ship our audit metadata data is just going to keep us covered. So if there's a problem with Kafka, we're still getting all of our windows through the API gateway. If there's, for some reason, a problem with API gateway, that happens, then we, of course, have our Kafka. And so if we look at it again, this is just everything we've discussed. We're going to produce that audit information through Kafka, but our metadata objects are going to go through the Lambda and through the Amazon API gateway as well. Cool. So now we have all of that information. We're producing it. We need to consume it at this point. And the audit window, we're going to consume using a simple Kafka consumer. And of course, if it goes through the API, we have a Lambda that parses it and stores it in a data audit table that we're going to discuss in just a few minutes. Now, the rest of the data that's arriving into RDR, that's already being consumed, right? So it's already in S3. We created a simple consumer that's going to consume all of that data off of S3, and again, store it in the same audit table. And if we've implemented all of these consumers on a single EMR. If you're not familiar with EMR is a service by Amazon that's called Elastic MapReduce. It's essentially a cluster, a bunch of servers running together. And it allows you to run several applications in parallel. So that's exactly what we've decided to do. And then again, in context, this is everything we've discussed. This is the entire data auditing architecture. If we talk about our data, it's still being produced through Kafka. It still arrives into RDR. And then we have our data auditing consumers. And then if we talk about the audit metadata, it's being produced through the Kafka, and then to a Kafka consumer, and then also straight through the API into the data audit table. Awesome. So now we have that information, we have it in a table. Let's start discussing about how we decided to store that table and how we actually designed it. And I think when we talk about data auditing information, you'll notice that it's pretty structured, right? Like it is structured. So we've just decided to store it in an RDS table using Postgres. So when designing our table, we first need to ask ourselves, what are the questions that we need answered? So let's start by talking about levels of granularity. We'd probably want to answer all of these questions in regards to a server, right? In regards to a process and in regards to a topic. That's really straightforward. These are all the points that we've discussed. What could be an interesting add-on? So we could also answer all of these questions on a regional basis, right? We said that all of our front-end layers are running on a regional, on data centers across the world, so they're regional. We'd want to answer these questions on a regional granularity as well. What else? What are other questions that we want answered? The first one is pretty straightforward. So arrival rate is just, for a certain time frame, out of the data that I've produced, how much of it arrived, how much of it ended up arriving. The second question there is a bit less straightforward. So it's arrival latency. So how much of the data that I've produced arrived within a certain time frame? How much of the data I've produced arrived within an hour, or within 3 hours, or within 5 hours? These are the questions that we wanted answered. These are the questions that we thought that would help us with our pain points. So let's look at our table. So we'll have everything that we've discussed. We obviously will have all of these data points that we talked about in our auditing information. The audit timestamp, the topic, the server, the process. What else? Well, we're going to have the event count, right? That's obviously our value. Just like what's the number, what's the amount of messages that was produced for a certain time frame. What about add-ons? So yeah, we've added a region column, and we've also added an insert time. Why insert time? Insert time will be the thing that will help us just calculate arrival latency. If you deduct audit timestamp from insert time, you're going to get that time interval that it took the data to arrive from the moment it was produced and up until the moment that the data auditing information was written into the audit table. And then also I have that location column there. What is it doing there? Well, we've decided to store all of our data in the same table. And so to differentiate if it's the metadata or the actual data, we've decided to use the location column. And so if we look at, again, an anonymized version of our data, let's just look at something. So if we look at insert time and window timestamp, I really want to draw your attention to the fact that they're all in UTC. That was especially important to us because that data comes from different regions. We have teams sitting in New York in the United States. We also have a pretty big R&D in Israel. So working in UTC was very, very important to us. We have topic name. We have the process ID. The region we were producing out of the server names. That is not best practice, but it was the easiest way to do it. Another interesting thing that I really want to draw your attention to is the event count. So you can definitely see different event counts there, like different numbers, right? But the interesting thing to notice is the 0. How is it possible that there's a 0 there? Isn't something wrong with the auditing system? The answer is no. So the way that we've implemented that auditing subsystem, the way that we were creating these auditing metadata objects, even if no data is arriving into that server, the audit metadata object will be created periodically every 5 minutes. So if no data arrived into the server, the event count will be 0, and then still that audit metadata object will be produced, will arrive, and will have an event count of 0. And that's awesome, because a lot of the times an event count of 0 can be completely normal. Maybe it's a dev server. Maybe we had lower data rates that day. But sometimes it can actually indicate a problem. Cool. So what you see before you now is just the logo for Apache Superset, and that's a BI tool that we use at Nielsen Israel for all of our BI needs. And so we decided to use it for our auditing subsystem as well. So what I have before you now is just the data arrival rate. So it's the data arrival rate for within 3 hours for the last month. And what's interesting to notice is that, yeah, it is above 100. It's 100 and 0.22. So there was definitely some data duplication going on there. And I'm aware that that's not really, like in the big data world, when we're dealing with such huge volumes of data, some data duplication, some data loss, that's totally fine. But when you see that number going above 150 or 200, you know for sure that you have a problem. Some more simple ones. So we have just like the straightforward data arrival for the last 1 hour or last 24 hours. And then also I have the exact query that these charts was produced with for you. So you can see that for arrival latency, we just deduct the window timestamp for insert time. And it's not really that complex of a query the moment you understand what's the data you're dealing with and how you're actually storing it. So what you see before you now is, again, the logo for Apache Superset, but it's also the logo that Superset use when they're running your query and loading data. And we were seeing that logo for like a lot of times. And so we definitely had a problem. And at this point, I just want to do a small shout out to my dad. My dad, who's been a DBA and a programmer for some 30 years more than me. And so when I came to my dad with a problem, I came to him with a query that was running for 1.5 minutes. He didn't give up, and he made it run for 10 seconds. So thanks, Dad. So how did we do it? How did me and my dad optimize PostgreSQL to run auditing data and to actually be able to query audit data? So the first couple of things we did are pretty straightforward. We decided to weekly partition our data. And we also decided to offload that data periodically to history. Why? Well, if you think about auditing data and log data, usually users don't really want to look back more than, let's say, a month. So you really need only that first month in hot storage. The second thing we did was also pretty basic, right? So we've defined some unique and complementary indexes on the auditing table, looking at the predicates that are most used for the queries that we were running. What else? Well, if you're using Postgres on RDS, I really encourage you to look at these 3 factors that I have on my screen right now. So these are not enabled by default by Amazon on RDS. And so you'll really be amazed at what can 10 workers do to your query instead of 2. So if you need if you have that need to run your queries in parallel and have better performance, look at these 3 configuration variables. And last but not least, I know that we all think that the optimizer of the database that we're using is the best and it knows best. But sometimes just tricking it will really improve the performance of your query. And the best example for that would be the in predicate. So if you use the in predicate and you have several, let's say, have several strings inside the in, it would be actually better to use a union with several selects. It will actually improve the performance of your query. Cool. So just to mention, I've mentioned that we decided to manage our partitions on a weekly basis. If you're wondering if Postgres 11 had that, has that possibility of actually just creating partitions when the data arrives, you know, it's a capability that a lot of relational databases do have today. The answer is no, they do not. And so we actually had to create an entire system based on Airflow that would manage these partitions for us. We did it by using standardized partition names. We had the week, the date of the date that the week begins with. We had it in the partition name. And so we used these 2 very simple queries and played with some dates just in order to keep creating these weekly partitions. And of course, offloading data to history. We've created a Spark job that would, again, run periodically, once a week, just offload that old information that we do not need anymore, calculate some statistics that we thought were cool and might be useful in the future, and store them in a data auditing history table. So now that we're done with that, let's go back to that end of the day question and see if we actually managed to answer it. See if actually the day's over. And yeah, we did. We definitely did. And I'll start off by explaining how you can actually get an answer. We've created an API our developers can use. We created a Lambda that would actually just make a calculation that we're going to go into in just half a minute. And that Lambda will give them back that answer. Is it the end of the day yet? Can I run my processors yet? So here I have for you the pseudocode of that entire Lambda. But don't worry, we're not going to really go into that pseudocode. We're just going to talk about the actual questions that we need answered. And these are the questions that we need answered in order to say if yesterday's over yet. So the first question is the data arrival rate for the entire scope. Because if we want a data arrival rate of more than 99% and it's 95 or 90, then yeah, the day's not over yet, I'm sorry. But let's say it is. Let's say it's 100. We're great. We're doing great. So data arrival rate, check. What is the next question that we need answered? The next thing that we're going to do is just check what's the number of audit windows that arrived for that entire scope. We're doing that as a check for our auditing system, because if our auditing system has stopped working, then we'll have a lower amount of auditing windows. And then essentially, we can't really trust it to give us a correct answer if the day's over yet. OK, so we have a high enough arrival rate. We also have a high enough amount of windows. We're good to go. But no, we're going to answer another question. So the last answer that we need is just the arrival rate for the last window. So when we talk about the last window, it's, of course, 11:55 p.m. Why do we need that answer? So if I can take you back into our charts when we saw numbers that are higher than 100, if we think about it, let's say that at 2 p.m. we had a really bad peak. We had a peak of like 150 or 200%. Then essentially, our calculation of data arrival by the end of the day will be skewed. And maybe we might get an OK answer for that. So we're just going to use that last window as an indicator and see that, yeah, OK. If the data arrival rate for the entire scope is fine, is the number of windows for the entire scope is high enough, if the arrival rate for that very last window is also just fine, then yeah, OK. Yesterday's over. We're fine. It is the end of the day. And so I'm really at the end of my presentation, so I hope that you guys are holding up. So let's talk about some alerts and add-ons. Using all of that information, we've managed to create an alert system on each one of the levels of granularity we wanted. And it really helped us pinpoint a lot of the problems that we've discussed in the beginning. So what would that be? If you have an alert popping up on an entire region, then the problem is probably not with your AWS Kafka or with your data loaders. It's probably with your view replicators. And if you have an alert on a topic, then probably the problem is not with your view replicator, it's probably with your data loaders. And so these alerts would look something like this. You can just actually run the query on your data and then straightforward send an alert to Slack. And this way, these alerts would actually arrive before any of our other alerts. Before an alert that the view replicator has crashed, before an alert that the Spark driver is not responding anymore, you will get this alert that the data auditing system has actually found a problem. What else? Well, remember how I talked about sequence ID and I said, yeah, that's a bit of a spoiler. What was it doing there? Well, at first when we started getting these high arrival rates and we said, wait, but a duplication, that cannot be. Maybe it's a problem with our data auditing system. So we decided that just to add a sequence ID into our audit header. That way, if you just query your audit headers straight from your file system and just group by that audit header, you can see if you had a duplication. If you group by your key using that sequence ID and you have you have groups with a number higher than 1, then you essentially have a data duplication. And last and not least, the location column. So I talked about the location column, and I said that we've used it only for 2 purposes, right? Just like the purpose of differentiating between our data and our auditing data. But we also always thought about just adding more locations, because our primary location was, of course, our Kafka, and then the second location was S3. But just adding more locations, more data points, would just provide us with more visibility about the way that our data makes through this entire waterfall. When is it late? And just give us more visibility and a better way to handle all of these problems. Do you have any questions? OK. So feel free to approach me on whatever platform you feel like you want to, LinkedIn, face-to-face. And thanks for coming and listening.